right, so here's sort of some of the just statistics that I compiled to just give you guys a sense of what's going on. The trend sort of continued, I think, where, you know, it's almost as if you took the exam one and just sort of compressed it on the middle, right? So we actually have more 90s. We have almost twice as many 90s this time as we did last time, and more 80s as well. So it sort of happens, right, that when things are going well for you, I think in this course, they really go well for you. When things struggle in this course, things really struggle. Unfortunately, the bottom, you guys can't see the bottom. I thought that this was probably one of the most telling. I looked at a whole bunch of numbers, and if you guys can see the bottom, you don't have to pay attention to the numbers so much. But this is the students that were right around average, from 50 to 60 on exam one. And what I thought was kind of really interesting is this was, I think, a microcosm for the course in general in terms of what is really happening, because, you know, students that were around the average really went in one of two directions, and in sometimes a very major way. You'll notice that there's a bunch of 80s, right, which is an A, right? So these are people that might have been around the average, and then something happened, maybe it clicked, maybe they were more comfortable with material the second time around, and they're really pushing up towards the top of the course. Whereas on the other end, you know, students really, right around the average of the first exam, really sort of started struggling in things. Perhaps it snowballed to the point where they were on the bottom end and really didn't know that much. But I also put this up here for sort of a second reason. You know, we're sort of past, I think we're past the drop deadline and everything else, right? And so I think whether or not you're going to decide to stick it out in this course or not, really at this point it isn't really an option. And so, you know, you might as well really gut it out and try to do your best to sort of improve in the course. And so what I put over on the sort of right was just sort of the dates, right? Sort of exam one was October 8th. A little over a month later was exam two. People increased their scores, some as many as 30 to 40 points from the first exam to the second exam. There's about the same amount of time between now and the final, right? And so people have done it, right? People have come from, you know, picked their averages up. It was quite astounding. I think I was looking at the numbers, and you know, people improved as much as almost 40 points over the first exam. And on the sort of reverse side, you know, people dropped as much as 40 points. So it's really, I think, a testament to how in such a short amount of time, a lot can sort of happen. And so, again, what does that mean? I don't know, sort of use it hopefully for motivation. You know, find out who those people were that had these improvements. Figure out what they did. If you know, if you're struggling, work with them. Try to pick their brains and so forth. I love I couldn't fix that, the October 19th group. I hate how Excel does that. You put like, you know, 10 to 19 and it changes to October 19th. But anyway, so again, here's just your sort of the sort of rough sense. I hate it, and like you can't. And I was sitting there, I was like, no, I want it to say 10 to 19, but that's not what it does. Anyway, so the point is, big spread. You know, I was, even though I know that there's a lot of people that struggled, I was, you know, it's really, I was pretty actually happy. I think with the scores on this, I think the higher end, there was actually quite a few people that this really starts to be clicking with. And so again, you guys have a month. The good news is that that we don't really have much material left, right? And so what that means is for those of you that might have not done well on this exam, you know, you can invest some time. I don't think at this point going forward there's a new set of material that you're going to learn that doesn't necessarily build on the stuff that we've learned in the past. Certainly there's a structural element to it. Certainly I think there's an aspect that students that do well on synthesis, right, where there's a certain puzzle solving element to it. The big thing going forward that's going to be a struggle for people is NMR structural determination. So what's going to happen is, in the same way, guys, quiet it down a bit. This is important. You guys have been through synthesis, right? And so hopefully you've either be convinced one way or another that you have to practice that, and it's a skill, right? It's not I'm going to watch somebody do synthesis and suddenly I'm going to be able to do it, right? It's I need to have all my ducks in order, right, and then really knock them down and spend the time and invest the time to actually get good at synthesis. And then even some people that I saw that were pretty good at synthesis, the exam comes up and maybe they have, you know, they have a small panic attack or something, and they can't necessarily think through. And if you're confident going in and you've practiced a lot and you feel good about these things, then oftentimes those types of problems won't happen as much. And so again, with NMR, it's going to be a lot of the same things with synthesis. So you have to sort of know the material. You have to sort of know the basics and the background. And then what you want to do is just practice the hell out of it, right? Just sort of problem solve, problem solve, problem solve, problem solve. Don't look at an answer and see the answer and be like, oh, I could have figured that out, right? It's, that's one of the other problems with organic chemistry is you see an answer and it makes sense after the fact and you convince yourself that you can do it. So again, it's important. I've got a lot of NMR practice problems online. Really what we're going to do today is we're going to focus on mass spec a little bit. But mass spec is not really something that students tend to struggle with too much. Certainly there might be an element of it, but really the big challenge moving forward I think is going to be NMR problem solving. So again, there's this element of problem solving that played itself out in synthesis, and so that same approach has to be taken towards NMR problem solving as well. Okay? Just sort of a reminder on this sort of regrade policy. If it's a blatant mistake, bring it by your recitation instructor. This is obviously if there's an adding mistake. If somebody we mistook a 7 for a 2 or something like that, or likely then you want to come to us and just sort of let us know that that's an easy fix. We don't need to go crazy filling out forms for that. Likewise, if there's an answer that's right, and it's been marked wrong for whatever reason, and that happens, just bring it to your recitation instructor first, because sometimes you might not see why the answer is wrong. Again, because the eye can sometimes see what it wants to see. So bring it by your recitation instructor as sort of a first one over, and then at that point either bring it to me or bring it to your recitation instructor. We won't have to go through the sort of forms. On the other side, if it's a partial credit issue, that's more subjective, right? And so that's not so blatant, and obviously, you guys are always probably going to, think that you deserve more points for an answer because, you want more points. So I would say that questions like that, I would just fill out a regrade request form, and certainly again, I don't want you guys, it's in your right to make sure that your exam was graded properly. So make sure that you take a look through it. I'll post the answer key when I get some time. Things are a little bit hectic right now, but when I find a moment, I will post the answer key online, hopefully by the end of today. And so just when you get your exam back, look through your exam, look through the practice exam, make sure there's no mistakes, count up, add up, make sure we didn't make any adding mistakes. And yeah, just let me know. Again, regrade request form is the sort of easiest thing to do. So with that, we're just going to talk about today. I've sort of got these PowerPoints, so I'll just sort of show this to you guys really quickly. All of the there's sort of PowerPoints for all of the different spectra. IR, again, you guys can look through it. I'm debating whether or not to even worry about it. It's kind of a, it's either there's a peak there or there's not a peak there. It's really not anything that's, who cares, right? Mass spec to the same extent, we'll talk about it a little bit today, but mass spec, at least in organic chemistry, what we use mass spec for is mostly, do I have the compound or don't I have the compound? Does the mass match, right, what I would expect it to match? And so there's some nuances within there, and I'll sort of talk about that, but the way that I often will discuss mass spec is we'll talk about the sort of theory behind it, and again, this course is all about problem solving, right? And so if the theory helps you, that's fine, but in truth, I'm not sure that within spectroscopy the theory is going to be really help you out too much with problem solving, if at all. So I'm not going to focus too much on the theory behind it, but more sort of on what an organic chemist, right? This is organic chemistry, so what an organic chemist sees as valuable. And by far the most valuable thing to an organic chemist is proton NMR. right? Every day we're taking multiple NMRs, and so you'll notice that the vast majority of what we finish up with here is sort of NMR, but particularly interpreting NMR spectroscopy, okay? So the questions that you guys will get, and we'll do some of these probably Tuesday to sort of get you guys seeing what kind of skill I want you guys to be able to build, is that you guys will get this sort of NMR spectra, and you'll be given likely a molecular formula just to help narrow things down, but what you'll have to do is actually figure out what the structure is based upon that spectra. And again, that's a fundamental skill for organic chemists. So, you know, I know that most of you guys are pre-med, but teach the course for the few of you that might become organic chemists. No, I mean that's what you do, right? But the others expect that the other sort of part of it is that, again, I think that the thing that I really like about organic chemistry, and I think the thing that really kind of pushes you guys, is the element of puzzle solving that's involved in it. And so certainly NMR has that element of puzzle solving. It has that sort of component to it that I think that goes beyond, I think, any specific course, but is more sort of life skill in terms of being able to process information, problem solve, and perhaps come up with solutions with things at that sort of level. Okay, so again, we've got these up here. These are basically ripped from the book, so you'll notice, and then I just sort of made some edits to them to sort of put it into perspective in terms of what I want you guys to know. Okay, and so here's, just open up the mess. Okay, so mass spec. So again, I'm going to go through this. I'm going to sort of explain the theory behind it. There's a little bit of issues about isotopes, and so I'll sort of put it in perspective in terms of how mass spec is useful. If we have time, you know, I think that and it'll hopefully become clear once we start talking about the fragmentations, but the area where mass spec is huge, and there's like one little blip in your book about it, and I would say read it, because I think to really understand and appreciate mass spec, you have to understand where it's had the biggest impacts. And so for organic chemists, certainly it's very valuable because we want to know what the mass of our compound is, right? But aside from that one number, you know, it's sort of more confirmatory. But in biochem, right, we'll be talking about fragmentations, and this is where mass spec is transformative. It's like, it's essential because what you can actually use in biochem and in biology is when you're talking about, say, for example, enzymes or any of these sort of macromolecules like enzymes and proteins and so forth. You can actually use mass spec to sort of understand the sequences to them. And so you have these huge macromolecules, and with NMR, right, NMR is really good for small molecules, but you can imagine as we start talking about NMR later on, it becomes a little bit too complicated. Certainly there are people that can sort of figure it out by NMR, but it becomes very difficult, whereas mass spec, and particularly this technique called tandem mass spec, really is crucial in biochem to sort of be able to characterize and understand enzymes. Okay, so with that, I'm just going to sort of go through this fairly briefly, but again, mass spec, as I just sort of said, it's the way that we sort of analyze the masses of compounds, and the way that we do that, as I'll sort of get to in a moment, is based upon the sort of mass to charge ratio. Okay, and so we'll get to what that means from time to time. Usually that mass to charge is almost directly reflected in the, yeah.
So mass spec is used to sort of, like, so you have an unknown enzyme, sort of.
Yeah. So I it's almost like I wish I would just do that. You know, I may do that next semester. It's just be like, here's mass spec. We're going to talk about tandem mass spec, which isn't in your book at all, but just to sort of show you guys it in a way that I think is more important. So what tandem mass spec does is, let's say you have, you know, a series of amino acids, right? It just allows you to sort of chop it up. We can talk about it later. I think it's fascinating, and again, if we have time, maybe I'll sort of show how tandem mass spec works, because that's really powerful, and that's where mass spec is like huge. In small molecule synthesis, like the stuff that I do, sort of your standard organic chemist, where we're like making drugs, small molecule drugs and so forth, mass spec is just used to confirm the structure. Here's the mass that I expect to get. What do I get? And that's why, you know, I just told you everything that if you were an organic chemist, you would need to know about mass spec, right, in that 30-second phrase. So we'll go through a little bit, but the general idea with the mass spec is, again, as you'll see, is based upon the charge. And so, again, that charge is generally 1, and so the mass that you're getting is usually directly related to the compound. But on occasion, you'll get molecules that will have, you know, say a +2 charge or something like that. And so in these cases, the numbers change a little bit. Okay, so here's sort of a general figure of what it looks like. Basically what you do is you sort of inject your compound, it gets ionized. Again, so we'll talk about more at the chemical level what that means by an ionization event. And the way that it's able to separate these compounds is by that charge. Okay, and so what happens is you have this sort of magnet that's in there, right? And depending upon molecules sort of shot and they're bent by this sort of magnet. Okay, and you can imagine this sort of inertia, sort of the heavier something is, if you think to physics, right? You know, it's going to be harder to bend it, right? And so if you got something that's heavier, it's going to move slower. If you got something that's lighter, it's going to be easier to move. And so based upon sort of size, right, you're actually able to, in this sort of little bending maneuver that's going on here, you're actually able to, they're able to figure out what the masses are. And there's a couple different ways, and then obviously it's sort of detected at the end. And as we'll talk about, you're injecting lots of different molecules at the same time, and so you're looking at lots of different molecules in sort of a series, again, of different fragments and so forth that you might see it, so that'll be a little bit more clear later on. Okay, so again, here's just sort of what the mass spec does. It will convert that neutral atom, as I just said, into a sort of into something that's more charged, and then separate those ions based upon that sort of mass to charge ratios we just illustrated. And then at the end, again, as you'll see, it'll become clear with the spectra. This sort of measure the relative abundance of each ion will become more clear once we actually start to see the spectra, and it'll hopefully make more sense why that would be the case. Okay, so what is physically happening if we think about it at the molecular level, right, is that you're shining electrons out at these compounds, and in general, this is sort of your standard ionization technique. That electron wants to be paired, right? So electrons like to be paired, and so when you sort of shine these beams of electrons at this molecule, what happens is it's going to rip an electron out of that system so that you have this new paired electron. And that result is that you have a sort of positively charged compound that's unlike anything you guys have seen, right? So this must look very awkward to you guys. What does that mean? Well, in fact, in any molecule that you have, you can sort of think about that electron where it's missing, it's sort of delocalized throughout the whole system. These are very high energy species. The way, and as we start talking about fragmentations, I want you guys thinking about it at least from the mechanism so that you can rationalize it. And so I think that the way that you can at least think about it is, well, where are those electrons going to come from? They're likely going to come from some valence electrons, and so whether it's lone pairs or, say, for example, a bond, maybe you guys could think about that bond being a single electron holding those atoms together. But again, we're talking at a sort of a level in terms of energetics and so forth, it's much different than what we're used to here. And so this should look very awkward to you guys, right? Hopefully we wouldn't synthesize this molecule with any of the reactions we learned, but at least in mass spec, these are the sort of components that we're looking at, and this is what we're going to use to rationalize everything that's going on. Okay? So again, the molecular ion, here's just the definition of it. You guys, I don't need to read through this. You guys can do that on your own if you want. So again, the other thing is, again, I'm not going to go through this too much. You guys can read this. It'll be on my website. But again, there's just different types of techniques that people use, and these different techniques each have their own advantages and disadvantages. Sometimes you can actually do positive ionization mode. Sometimes you can do negative ionization mode. But that's that. Okay, so where I care about this, for your guys' sake, is to sort of put it into the perspective of the organic chemist, like, again, where we might use this. And so what I'm talking about at first, and I'm going to sort of put this in the context with a couple of different types of spectroscopy, there are different levels of resolution to the mass spec that you can get. So depending upon how high quality of a mass spec that you can get, so you can imagine in that contraption, how defined that is, you may get different levels of resolution. So if you can imagine having molecules that are, for example, low resolution, you might only have, say, to that single sort of, 25. It's not going to go 25.0054. It'll just be 25, and that's the extent of the readout that you're going to be able to get. And so that can be useful when you're doing chemistry, where you're maybe adding things on the molecule where there's a difference in the molecular mass at this sort of level. So here's just your standard nucleophilic substitution reaction. And so if you were to run this reaction, you could sort of use low resolution mass spec and sort of get a first approximation for what the mass is. Now, where this is actually really valuable for synthetic chemists nowadays is in your lab course, you guys have done chromatography, yes? You guys done GC? Gas chromatography? Okay, so there are instruments that are actually really valuable. So if you're running a reaction, let's say, and you're anticipating a reaction to be generated where you're getting a new mass, right? And you just want to see if the chemistry is working. Oftentimes, what we will do is we will take our sample and we'll inject it in a GC-MS. So you guys remember you had the GCs and you would get those traces. Well, what you can then do is you get these new peaks. And when you guys got the peaks, it was like, oh great, I got a peak, right? But when it's in tandem with a mass spec, what you can do is you can actually click on those peaks and you can actually get the mass, right? And so that could be, you can imagine that's going to be really valuable if you're trying to carry out a reaction, you're trying to figure out something and whether or not it works or not. You run your reaction, you inject that thing onto a GCMS, which is, again, just this tandem. We also have an LCMS, which is liquid chromatography. It's just if your stuff doesn't go to the gas phase. And then, and again, that's going to be really powerful for sort of first approximations, yeah.
So if you put acetylene inside a mass,
well, that's a gas, right?
Right, but if you put that with the negative charge inside a mass spec,
That would be bad. Yeah.
Oh, okay.
Yeah.
Like in terms of like, let's say you could do it,
right?
Like a neutral charge.
Then you wouldn't see anything. Because you need the charge in order for it to bend, right? So you would need that charge. So I don't know exactly what might happen. You might just get the readout of the negative charge, right? You know, the stuff that doesn't get ionized at all, you might see if it was in a, sort of a negative ionization mode detection. But yeah, so again, this is just the point. This is obviously an oversimplification of the reactions that we would perhaps run, but hopefully that gives you an idea. And you know, this sort of idea of using to sort of, especially for like monitoring reactions, if you're looking at a reaction and you're trying to work something out, you know, to be able to know the mass right off the bat for a synthetic chemist is actually really valuable. And I had a friend of mine from Yale, who's a professor there, Seth Herzon, came out, and when he was in grad school, he was TLCing everything, and you know, I was talking to him, we were having lunch with him and some of the students, and he was like, he never does some of these basic techniques. Every reaction just goes directly onto these LCMSs because it just gives him so much more information. It really helps him. He's making these monster targets and really is sort of a huge synthetic chemist. And so that's kind of the stuff that he does, and that's how powerful this technique is for somebody like him that's constantly trying to develop new reactions on complex targets. So it's really valuable in that extent. For most organic chemists, when we do chemistry, again, that can be really valuable at the low res standpoint, but we'll talk about NMR a little bit. By and large, NMR is our go-to. So usually what the mass spec becomes, like when we have to characterize molecules and so forth, is that we need to get, as part of our characterization, we need to get an exact mass. And so the exact mass is a little bit higher resolution. It's a little bit, certainly it's obviously a higher, a better, and more sophisticated instrument, but it can actually tell the difference at sort of low molecular masses. And I'll get into what this means in a minute, but so let's say you have these two molecules that I've shown here that have the same AMU, perhaps at low resolution, but at higher resolution you can see that at these sort of decimal points they actually vary. Okay, and so how it does this, right, is that you can imagine, you know, when we think about AMUs or sort of masses of some of the elements that we have, we often sort of think about the average masses, but we have to start thinking about the isotopes a little bit, and certainly the isotopes have a specific mass, right? And so C13 is going to have the same mass, right, as across the board as every other C13. C12 is going to have the same mass. So those isotopes are all going to have identical masses, right? And so when you're actually looking at the exact mass, you're looking at that specific molecule, right? And so that specific molecule isn't going to be made up of an average, right? It's going to be made up of C12 and 5 C12s and 2 C8 or 2 hydrogen, you know. And so if you start adding them up, right, with those sort of the major isotopes, right, that's going to be your sort of major peak. It's going to be comprised of all of the major isotopes of every element that you have in there. And you can imagine as you start looking at some of those masses that are more specific, you're going to get a value that's going to have, multiple decimal points, and it could vary at those multiple decimal points. And so high-res mass spec allows us to look at that level of resolution, and so that we can actually distinguish between some of these. It's never so specific. There is a little bit of variability, but there's we have to have it when we are putting together our characterization. We have to have it within a certain area. Yes, Owl.
The high resolution, because it gives the mass, which helps identify them.
Yeah. So
that's what it does.
So that's exactly it, right? Because there's probably only so many, so it can certainly give you that molecular formula. There's actually software that you can use where if you put in, it's just adding these up. It's nothing too
where
fancy.
The low resolution just gives you the EMU, which
Yeah.
is similar to something else, so you can have
Exactly. And so again, there's programs, it should be real easy. You're just adding up all the things, right? But you wouldn't want to do those all manually. But so there's programs where if you put in a specific molecular formula, you'll get the exact mass. And then what you'll do is you'll look at the mass spec and you'll be able to confirm. And so for a synthetic chemist who we are trying to make a specific compound, right? When we have that compound, we're sort of using this to confirm it. But you can imagine if you're, say, a natural products chemist, right? You've just identified this new compound out of a plant. You have no idea what the structure of it is, right? And you're trying to get as much information as you can to sort of solve that. And so what you might be able to do is you might be able to get a high-res mass spec, and then that will give you a molecular formula to work with. And again, when we start doing NMR solving, when we start solving NMR structures, you will get the molecular formula, right? And so you could almost imagine that would have come from a high-res mass spec. Okay? Okay, so that's that for here. And it's not always, again, that the point to be brought up is that it's not always the case. This actually rears its head from time to time more than you might think. It's not only, the previous example I showed you was an example where you actually had some different elements in there, but you can imagine even a molecule which is carbon, hydrogen, and oxygen, right? They can even have differences, or they can have similar sort of quote-unquote nominal masses, but actually be different at the molecular point. So certainly high-res mass spec can be valuable to this extent. The other thing that this sort of isotopic ratio can do is that you'll notice that many of them, right, hydrogen, carbon, nitrogen, oxygen, so the ones that we sort of classically think of as the big, these are the molecules that we basically work with most of the time, right? By and large, there's a major isotope that's overwhelmingly a major isotope, right? Carbon, C13 being roughly about 1%, right? And so you can imagine that you're not really going to notice really anything special about that isotope. But there are some isotopes where it's not that drastic of a major isotope, and in these cases, mass spec can be a little bit useful as well. And so I sort of shown sulfur, chlorine, and bromine down here, right? And you'll notice in these cases we start to get numbers that are a little bit closer. Again, this is still mostly sulfur 32, but there's an amount that you might be able to see of sulfur 34. But particularly with chlorine and bromine, now you start to see much more dramatic things. So again, chlorine 35, chlorine 37, now we see about a 3-to-1 ratio or something like that. And in bromine, we see about a 1-to-1 ratio, right? And so you can imagine that if you were to take a mass spec, right, like here's one of chlorine, right, ignore this, this should be 37. I screwed up the math there. But anyways, so this is the major mass of the compound, right? And you see these two peaks of 64 and 66. And what these correspond to is really the molecules that have the two isotopes of chlorine, right? And so the major one would be chlorine 35, and the other one would be chlorine 37. So that should be 37. The other thing that you notice is that radicals, bromine and chlorine are both radicals, and we'll get back to this in a moment. Those can fragment readily, fairly easily, and so you'll often see when you have a halogen, another sort of indication that you might have that element in there would be that you see a peak of 29. Right, and that 29 corresponds to the sort of positive charge of everything besides the chlorine. Okay, and so you can imagine a similar thing with, say, bromine. So here's a compound with bromine, and again, you see this sort of 1-to-1 ratio. And so there are, yeah.
M to Z would be mass to charge?
Exactly, right, mass to charge. Right. And again, and sort of here's your spectra, right? We have sort of relative abundances. And so there's lots of things. Mass spec can be kind of messy, so you'll see lots of other peaks, and sometimes it's difficult to figure out what everything is, but you usually will often look for some of the major peaks, okay? And so here, again, you have a molecule. We'll get into fragmentations in a moment, but again, here's a molecule that has bromine. Bromine fragments and leaves really quickly, right? And so you see the major peak is actually 43, which is the sort of M minus bromine, right? But again, down here, sort of the parent mass, you see those two isotopes at about 1 to 1. Okay, so the point is that oftentimes you can sort of know whether or not you might have a specific isotope based upon whether or not you have a ratio. You know, sometimes you can see sort of these ratios that can often be kind of telling of what a specific element might be in there. Okay, so sulfur, whatever. Okay, so when you're interpreting mass spec, again, I'm not going to give you guys, you know, we're not going to go too crazy with mass spec, but as we'll discuss more in terms of fragmentations and so forth, there are ways that, and there are things that you can do where you can start getting some information from mass spec that could be useful. And here's some of the things, and we'll probably go through this a little bit more. This sort of is the mass of the molecular ion, odd or even. We'll probably go through this a little bit more with NMR. This I'm not going to worry about too much. This is just a sort of a math issue. Again, you guys could read through that. If you sort of just add up your stuff with a molecule that has nitrogen, you'll sort of notice that it's always, zero or even. It'll have an even mass, but anytime you have sort of an odd mass, oftentimes that can be an indication that you have a nitrogen. I'm not, that's not really, it's just that nitrogen is one of these common ones that you see up again. So again, if you have that positive mass, but I don't know that that's really going to be that useful. Okay, so the other thing that we're going to sort of get to is the sort of second part is these sort of fragmentations. And the fragmentations, again, this is where MSMS, this sort of tandem mass spec comes in and why it can be valuable. But you can imagine as we sort of saw all these other peaks that were going on, by and large what these are fragmentations, right? Where these very high energy species, and at these high energy species things can happen. Certainly we've seen sort of drawn them as these positively charged radicals, and so you can start to get rearrangements. And so again, they're unstable and things are going to happen, right? And some of these things can be as simple as, say, M+1, right? So you'll often see a sort of an M+1 peak, because what will happen is, remember we sort of drew this compound here, and what can happen is that's not something that's, one proton's not really going to hold together or bond too well, right? And so what will happen is it'll just kind of fall apart, right? And what you'll get to is sort of two possibilities, right? Because that radical could go with either side, right? And so the radical could stay on one side and the proton could go on the other, right? Or you could have the positive charge on this guy, and you could have the radical sort of on the other one. Okay? So, as you might imagine, right, in terms of a lot of the things that we've learned, in terms of cation stability, can also play itself out with these sort of fragmentations, right? So we're going to be generating a carbocation on one end, and the radical is going to be on the other. So oftentimes what happens here is that we get the radical, when the bond's going to break, what's going to happen is the electron's going to go to the element that's less likely to be able to stabilize that positive charge, right? And so oftentimes what we'll see, and again, that's the one that we see, right? So if you go back to this compound here, if it were to fragment, you wouldn't see, this goes back to what I think Saeed was asking before, right? You're not going to see this, but you'll see this, right? In this case, you'll see this, but you won't see this. So you won't see the radical, right? You'll only see the positively charged species, right? Because it's only the positively charged part that you'll see. So when you get this fragmentation, you might not see the other piece. You'll just see the charged piece, and so that can be kind of important, okay? But again, this trend is going to go in terms of if you're going to break a carbon-carbon bond or something, the way that it's going to more likely break, right, you'll get some ratio because there's so many that's going through, but the way that it'll more likely break will actually be similar to what we've seen with, say, Markovnikov, right, these sort of things that lead to carbocation stability. And so here's just sort of your general trend. This is just the one that I took from the book. I wouldn't worry about memorizing this per se, but just sort of remember primary is less stable than secondary, is less stable than tertiary, and there's some stabilizing factors. And so you should be able to reason why you might see one fragment more so than another, and you can sort of reason that based on carbocation stability. Along those lines, again, fragmentation tends to occur in the middle rather than at the ends. That should make sense, right? Because likely if you're going to break, say, for example, let's say that you have a carbon chain, let's say you have hexane, right? While that single bond breaking, right, might favor a carbocation on one end versus the other. You may also be in a situation where you have multiple bonds that you could break, right? And so certainly, if you're breaking a bond, right, you're really creating two groups that you kind of need to be able to stabilize a positive charge, right? So a radical we kind of think about as being electron deficient as well, right? And so if you can imagine if you have, say, hexane, right, you might not see the end fragment because then you would have to generate either a methyl cation or a methyl radical, right? Whereas if you broke one of the ones in between, then you would be something that would be more stable for both the radical and the cation. Does that make sense? A little bit, right? So just think about the fact that we just talked about how cation stabilization would, if you're looking at a single bond, which way that's going to break is going to be dependent upon which one's going to have the better carbocation character. But your molecule has lots of bonds that can break, right? And so the choice, and again, all of them could, right? And all of them will to a certain extent, but some will more than others, right? And so the ones that are going to more likely break, right, are going to be the ones that, where both, you know, the radical can go to one end because that's got to be more stable, and the cation's got to go to the other one, and that's got to be more stable. So sort of internal carbons, or anytime you could break a carbon where sort of both of those sides might stabilize a positively charged compound. This should make sense. Let me just. That's why I hate PowerPoint, because you can't explain stuff, right? So if you have a molecule like, say, right, so let's say you have a molecule like this, right? It's going to fragment. You're going to get lots of different fragmentations in this molecule. You might see some CH3s, some M minus CH3. You might see a lot of these other things. But as you can imagine, if you think about a few of the different cleavage, or some of the few different breakages, right? We'll go there, and we'll go to there. So we'll just say A, B, C, right? And so if we sort of look, I'll draw these each as sort of partially broken, and then I'll fully break them each, right? So in the case of A, right, you're sort of at right, something that might look like this. Again, we're going to rip that electron out of this bond here, right? So pulse it with an electron. The electron's going to go in there. It's going to come out as a set of electrons. And so what you're going to end up with this species here, right? This guy can go in one of two directions. In this case, both of them are roughly equivalent, right? Because they're both secondary. And so likely what you'll get is a 1-to-1 ratio of this mass and this mass, right? Does that make sense? But there's other fragments that can take place as well, right? And so you can get, say, for example, something like this. Right, where we sort of rip that electron out of this bond, right? And again, when this bond fragments, right, the electron's going to go to the one that's going to less likely stabilize it, right? So we'll go that one. So this, you'll more likely see that cation fragment. So that's the fragment that you'll see, again, the cation, because that one would more likely stabilize it, okay? But you would see these two fragments probably more so, right? Because this bond is going to just, in general, whether the radical's here or the radical's there. In this case, you've got a radical on that sort of methylene carbon, right? Yeah.
The second one, you have like a hydride shift, make it tertiary.
Yeah, lots of things. Yeah. Yeah, so that's one of the things with mass spec, right, is that a lot of things can happen, but this is what would happen first, right? And so you might start thinking about it in terms of kinetics, right? You might not have time to do that, so it might rather go to the other one. But yeah, that's, sure, yeah. And then in terms of on C, you might expect that to be the least of all of them, right? Because in this case, what you're doing is, right, when you sort of fragment this bond here, right, you've either got to put a carbocation or a radical at that methyl group, and that's going to be the least stable of them. So when we're talking about branches, this is going to be the least likely, right? So this will probably be the least likely. This one might be the most likely. You'll get a 1-to-1 ratio perhaps of two of these, right? But at least the fragment from this carbon-carbon bond might be the most likely, right? Because what you have is two secondary groups that would otherwise stabilize that, right? And then meanwhile, this one would probably be somewhere in between, and you likely wouldn't see any of this one at all you'd probably only see this carbocation. So again, just sort of think through it just in terms of thinking about this stuff, just kind of think about when you're sort of ripping out that electron and it's breaking down, which one might be more likely to form. Okay? Again, this will be on my video, so I gotta keep going. Okay, and so here's an example of that, right? So I guess I didn't need to draw that stuff on the board. Well, that was fine. So here we have, again, a long chain compound, right? And as you sort of look at the spectra, what you notice that you really don't have that much of is what the methyl one would be. So what would the methyl be? It would be 12 plus 3, 15. So you would expect to see a peak at 15 that would represent the methyl cation, right? And you actually don't see any of that at all, right? Because that's not going to be that stable. Okay, so does that make sense? And meanwhile, even the, the sort of other side, right? So if you could imagine simply breaking the methyl group and going to the other side, then you would have, what's the mass of this? 114. So 99, right? So 99 would be, is that right? Did I do that math right? Yeah, 114 minus 15. 99, right, would be if the cation went to the other one, right? And the radical went to the methyl. And yet we don't see anything at 99 either, right? So that fragmentation on the end isn't going to be likely because you'll either be putting a methyl group or a radical, right, on a, sorry, you're either putting a radical or a cation on that methyl group, yeah.
What if you had like an alcohol at the end?
We'll talk about that a little bit because certainly, what would you expect?
I think that
Question is if there's an alcohol at the end, if it's not just a terminal methyl group, what would be the expectations about the stability of that breakage?
well, it would be more stable to the oxygen capacity, possibly.
Right, with the cation. Not with the radical though, because then you would break the octet rule. But yeah, with the radical you would, yeah, so absolutely. And then we'll get to that to an extent, so that's absolutely right. So again, just use your, what you've learned today, and this should sort of make sense, right? All right, and again, that peak at 43, I wouldn't read too much into the fact that one's really big. I think, if I remember right, I think that's just a statistical, I think there's a couple different ways that you can make it 43. Yeah?
What is the significance of the peak? What is it supposed to be?
Right, so when you get, maybe I wasn't clear about this before, so when you're sort of, go back to that second figure we saw, right, you've got the sort of mass spec, tons of molecules are going through there. Right? And so lots of different things can happen. And you're not only going to get the best thing to happen. You're going to get a mixture of all these things. You're at a very high energy state. There's really not too much of an energetic difference that's going to make it go to only one or only the other. But there are subtle differences. And so the reason why you see all these peaks is these represent a lot of the different possibilities that could happen. Right? And that's what I was saying. One of the possibilities would be that methyl fragment on the end, and yet we don't show up here, so you can tell how poor that is. But there's a lot of other things that can happen here, and there's a lot of other fragments, and you end up seeing all of them. And again, and there's some little things in here, and there's sort of side ones that, that might represent smaller things, maybe hydride shifts followed by other things that we're not going to spend too much, that I actually don't even know about. But yeah. So the relative abundance. Right? Oh, yeah, because it's kind of, the scale's kind of. I think that they're just saying that relative, this is the major one, and then sort of anything else would be number based on that. Usually, I don't even know what the number is. I wouldn't worry about the y-axis too much. I mean, that's just, the point is that how high these are, max, and, how high this is just represents how many molecules like that went through. And so the higher the peak is, the more likely that fragment happened, right? The more often that fragment happened. And so as you might expect, there may be some reason why that one might be the most stable, and it could be for things like resonance stabilization or something else. Okay, so now, in addition to some of the quiet down guys, this is where we start getting to a little bit more, I think, tricky mechanisms. This is where we're going to start getting into bigger fragments. Okay, on occasion, fragments can happen. I'm going to show you guys just a few of these. Certainly there's a lot that can be out there, but I don't want to go nuts thinking about all the different fragments that can form. But the important point is that in addition, again, we're at a very high energy state. As you might imagine, things can start happening. Fragmentation, additional sort of eliminations, additional rearrangements can start to take place, and they can sometimes bear themselves out. And so oftentimes you'll see something that might not just be as easy as, oh, break this bond in half, oh, break this bond in half, right? There might be a peak that might represent something different. And there's some standard ones that you'll see on occasion, and we'll go through those. And as I've sort of drawn, I've sort of drawn it, this isn't in the book this way, but I want you guys thinking about it a little bit in terms of what we've seen in the past, and so we can sort of think about it in terms of our homolytic bond forming and bond breaking mechanism. So as you could imagine, right, if you've got a molecule that, say, for example, has this radical, right, the radical is going to go to one side, the cation is going to go to the other, right? And so as you sort of look at this, right, if the radical is going to go that way, you're going to get a cation there. What can happen is you can start getting the species that look like this. You can actually start to eliminate, like in this case, you're actually eliminating ethylene, okay? Your ability to predict this, you know, there may be a few specific ones that I'll get to, but you know, what I would more be interested in having you guys do is if I, say, for example, showed you this and said, oh, and a fragment was observed that was this, you know, how did that fragment form? And so you should just be able to sort of think about, practice. I think it's a good way to sort of practice homolytic bond cleavage reactions to get to some of these. Okay, so you can sort of think about it like a mechanism problem. Okay, but here's just an example of where you start seeing peaks that might be a little bit different. Don't worry about that. Okay, so what we're going to go through is a few functional groups. This kind of goes up to what was asked before about if you have an alcohol on a specific point. So as you might imagine, there are functional groups where oftentimes the stabilization of whether it's a radical or a cation might bear itself out on a particular type of sort of rearrangement, okay? And so here's an example of a molecule, right, where you actually have this sort of structure here, right? So again, remember that this could likely be at any position on that ring, right? But it turns out that usually, as you might imagine, where you're going to end up fragmenting, right, is going to be where you might get carbocation stabilization, right? So as we're talking about, and again, this just goes in line with everything we were saying before about where are we going to break that bond. If you have a group that has an alkene in it, right, when it breaks, it's going to want to break to the one where you're going to have there's a major breakage point. It's going to be that point where you have a carbocation that can be stabilized, right? And so if you have an alkene in that molecule, one of the places where that carbocation can be stabilized is the place where you would have what? Resonance stabilization, right? And so, again, if you have an alkene, it's going to fragment. Just sort of think about where it can fragment and where it can have its sort of radical stabilization. So again, here we have a molecule that is 1, 2, 3, 4 butene, right? And so, so in this case, the sort of one of the major fragments that you see, right, is this peak at 41. And so let's say, for example, you knew that you had a butene, right, but you weren't sure, for example, where the alkene was in the molecule, then maybe the sort of fragment that you might see might help you sort of know, right? And so, or if you had a long chain alkene, right, you could imagine a situation where you had, say, this is why I never do PowerPoint, ever. Right, so let's imagine you're in a situation, right, where you have, you know, you've just made some hexene, you've done an elimination reaction, turned out that it was a synthesis problem and you guys were in a situation where you had 2 eliminations and you separated the 2 and you wanted to know sort of where that alkene was, right, and that could have been, it's either going to be this molecule or, say, for example, right, so you've got this mass spec, it's turning up what you would think that it would, perhaps the NMR is a little bit difficult to figure out, right, and so when you're looking at this, you might be able to use the sort of major mass spec fragment to be able to figure out what the compound would be, right, and so if it were to be this molecule here, right, you might expect to get a fragment where you have, I'm not going to do the math, but you would expect that to be your major fragment, right? And in fact, you might expect to see 2 of these, right? Because the same fragmentation on the other side would lead to the same molecule just reverse, right? Or in a situation like this, right, you might lose m+1, right? So you might just have the mass minus 1, right? because in this case what you have would be a carbocation here. And on the reverse side, what you might get is this molecule shown here. Right, and again, I'm not going to go through the masses, but you can sort of perhaps use this sort of alkene, again, where you might use this sort of stabilization to be able to predict, based upon a specific mass you get, where that mass, where that, say, for example, alkene might be. Okay? So again, this should just fall in line with what you guys think about in terms of your chemistry, in terms of, think about cation stabilization, think about what we sort of learned earlier. Okay, so the same thing as you might imagine would happen with propargyl groups. So in this case, it's an alkyne rather than an alkene. So an alkene, that would be an al stabilization. With an alkyne, it would be a propargyl stabilization. And so again, I'm not going to spend too much time doing this, but as you might imagine, the propargyl group can also stabilize carbocation character through this sort of process here. Okay, so I'm going to finish up with a few of the more, I think, complicated rearrangements. And again, whether you can predict these in, say, for example, an NMR or in a mass spec problem, where you can anticipate these forming, I think is kind of unlikely. I do want you guys focused on NMR, as I've sort of said. So I think the level of being able to predict that these things would form, I don't really like that much. How I normally teach this component is, again, sort of like a mechanism problem, right? And so what I think you guys should do is, if you see, I would likely give you this and ask you guys, how does this fragmentation take place? And so that's, I think, a better question to ask, because that's going to get you guys practicing moving electrons and so forth. And again, there's a couple different ways that you can draw this. And so this would be, if you have, say, a cyclohexane. Okay, this is what's kind of formally a retro-Diels-Alder. Okay, so you're going to learn this a little bit. You're going to learn about Diels-Alder reactions next semester. And so this is the sort of reverse of a Diels-Alder reaction. But again, I think it's often best to think about it. So the book will sort of show it like this. I think it's better to sort of think about it in terms of what more likely it might be happening, right? It's a homolytic process. You're ripping an electron out of the species, and so to sort of think about that cleavage being from a homolytic standpoint might be a little bit easier to do. And so here's just sort of an example of that, okay? And I know there's a lot of arrows there, so just sort of map it out. Okay, heteroatoms, as sort of we just stated earlier, so you might imagine as alkenes and as alkynes can sort of stabilize and have these sort of effects that can sort of stabilize resonance and so forth. It turns out that heteroatoms, specifically, when we talk about heteroatoms, we're particularly talking about nitrogen-containing molecules and oxygen-containing molecules. These have lone pairs in them. Okay? And so in addition to some of the stabilizing effects that might happen through resonance, another thing that can sort of bear themselves out in here is that when you're going to extract if you're going to extract an electron out of here, if you're going to rip an electron out of this system, oftentimes one of the places where those will come out of will actually be the lone pairs. Right? And so, again, if you sort of think about this molecule that you might draw here that might represent all the possibilities where that electron might be gone, one of the ones that you can think about that will play itself out, right, will be if you just have a sort of a lone pair, you have a single electron rather than a lone pair, so this sort of single electron radical-like cation that we see here. Okay, and when you get to these, right, you can imagine things can happen, right? And one of these is effectively what we'll often call, there's different names for this, but you can imagine this being kind of a, I don't know if you'd call it an alpha cleavage. What do they call it here? But just sort of look at the mechanisms, right? If you have that lone pair here, this is kind of similar to an elimination, right? You're going to bring that lone pair down here, break that bond, and you'll get a radical up on the other guy. And in this case, what you've got, right, and the reason why it would fragment this way, right, is in part now you've sort of gained some resonance stabilization here, right? And so this sort of carbocation character, so you see the positive charge in the oxygen, where you have this double bond, and now you have this sort of resonance stabilization. So again, when you rip an electron out of the heteroatom, you can see these fragments that I've shown you here, and again, it's partly because you generate these sort of resonance stabilized oxonium species. And so, again, in the same way with, say, an alcohol, right? So yeah, so that's going to get the problem solving, right? And so you have to have some information in a mass spec problem, right? To just be given a mass spec and say figure out what the structure is, I'm never going to ask something like that, right? That's not going to be something that's going to be asked. I think more than likely, I want you guys to get familiar with these fragmentations, and I'll ask a question that might be directed towards using that fragment to answer it. And so I'm going to sort of show you another example. So pay attention to kind of the problems that I'm putting up here, because those might represent, I think, the types of questions that I think would be fair game in terms of mass spec. And again, I don't want you guys going nuts on mass spec, because I do want you guys, NMR takes a lot more, there's a lot more information at NMR, and that's the one that you're really going to have to work to get yourself sort of thinking about it. So I would treat mass spec maybe with a little bit more effort than perhaps IUPAC, but not much more, if that makes sense. Right? And so again, we talked about it with alkenes, right? But you can imagine, let's say you had a couple of different molecules, right? Let's say you had these two alcohols, right? Again, exact same molecular formula, right? And you wanted to sort of know which one you had, right? So, again, perhaps you made these from the alkene, right? And you got a mixture of the two, and you were and you separated them, and you wanted to use mass spec to try to figure out which batch was one alcohol and which batch was the other. Again, what you would do here, right, is you would probably look at this sort of fragment right around here. So, right, so we're looking at, if you can imagine that radical here. Right, and so the part that we would be looking for might be this way. So whatever this would add up to, the mass of this, right? Or perhaps the mass of the other way, which would be right? And so you would see these two masses, for example, right? And so that, if you saw the presence of fragmentations that would correspond to these two masses, might be an indication of this one. There's some symmetry here, right? But in this case, what you would expect to see, and again, you guys can go through the mechanism on your own, but you would expect to see the mass of that one, okay? And so, again, the fragmentations, specifically when we're talking about functional groups, I think, if you're sort of looking at two, and you have a couple different mass specs, and you're asked to match which one is which, you would sort of look at what some of the standard fragmentations would be, and that might help you solve them. So you would have some information. And again, I think this would be the level of question that you might get on, say, the quiz, right? It would be, you have these two alkenes, here's a mass spec, which one of the two alkenes might it be, right? Or something to that extent. Does that answer your question to an extent, sir? And we'll have again, what we'll probably do is, I'll go through maybe, because I do want to get to NMR fairly soon, because I think that's going to take some time for you, but maybe what we'll do is, we'll go over some mass spec problems that might be up the alley, just to sort of get your mind thinking about how mass spec could be useful in problem solving. But I know it's difficult. I know it's very difficult to sort of process all this information and be like, what do I need to know? There's so much here. What do I need to know? And again, it is spectroscopy for the organic chemist is problem solving, right? It's here's the spectra that's going to help me figure something out. And so it's always, any question that I ask is going to be sort of in that realm. But you're always going to have some information, right? It's like, again, we'll get to NMRs and you'll always be given a mass, molecular formula. And the reason is that without it, it's too difficult. And it's kind of the same thing with mass spec. By itself, it can't be, it's sort of difficult. Okay, so here's just an example of that fragmentation, right? So again, you can sort of think about it as heterolytic bond cleavage, or you can think about it as homolytic bond cleavage. But here's just an example of the spectra. Again, this is butanol, right? And again, you see two potential fragments, right? The one would be for the one that I was just sort of showing you guys, right? Which would be the AMU at 31. That'll be the major mass. The mass, did I show you guys this? The other one, I guess I'm not going to talk about this that quick. The other one that you'll see from time to time is the other important point to bring up about alcohols. And so let me just sort of revisit alcohol really quickly. You'll see, anytime you have an alcohol or anytime you have an ether, you'll often see the sort of loss of that entire fragment, right? Sort of usually but it usually leaves water, okay? So oftentimes what you'll see is you'll effectively get an abstraction of a proton nearby, right, at the basically 2 carbons away, right? So oxygen, carbon, carbon, hydrogen. You'll see a fragmentation to form a bond between that oxygen and that proton, and then you'll see sort of like loss of water. And so mass minus water, especially when you have alcohols, is fairly common as well. So that can be another indicator of an alcohol, is that you'll see mass minus water. Not sure where that's going to really come up too much. Okay, as you might imagine, in the same way that oxygen-containing molecules might have these fragments, nitrogen-containing molecules would have the same type of thing. So what you see in alcohols, sort of, just think about that in terms of amines as well. And so, again, in the case of the amine, this is actually going to fragment pretty quickly, right? So, like, in this case, that's the parent mass at 87. You don't even see it because that fragmentation takes place so quick. Part of the reason is that a nitrogen is able to stabilize a positive charge fairly readily. And so, again, in this case, what you see is really the biggest peak in this entire molecule is actually 30. And so, it's extremely fast in sort of this case. Alpha cleavage of carbonyls. Okay, so this is where tandem mass spec comes in. So if I have some time, I'll sort of show you guys a little bit about tandem mass spec and where that can be useful. But carbonyl cleavage is often some of the best and perhaps some of the most useful cleavage that's out there. And you can sort of rationalize this in the same way that you think about other heteroatoms as well. Right? The idea is that when you have a carbonyl, in the same way that I sort of showed breaking those 2 bonds near the alcohol, you can do the same thing with carbonyls. And so as you sort of seen here, depending upon which carbon-carbon bond you're cleaving, you're going to get to 1 of 2 masses. And so you could expect to get and see these 2 fragments as well. And again, from a mechanism standpoint, you can rationalize it from that ribbon on an electron, right? And just thinking about homolytic bond cleavage to get to these species. And again, that sort of oxygen is going to bear that positive charge, and that's going to be the one that you're going to sort of see. Okay? And so again, here's sort of a spectra of this. Again, here's just a molecule, and again, as you notice, a lot of the things that will happen, as you might anticipate, right, of these 2 cleavages, one is going to be more pronounced in the spectra than the other, and the one that's going to be more pronounced likely is going to be the one that's going to be more stable, and it's going to have more stable carbocation character. Excuse me, let me take that back. There are 2 components, right? And so this goes back to what we talked about earlier. So when we were talking about the branches, right? When we were talking about branching, we talked about how, the carbocation stabilization is the most important, but given a couple options, you might want to look at the radical stabilization as well, right? And so this is sort of what you're seeing going on here, right? So you're fragmenting the carbonyl, but not only do you have these components here, which might be equivalent in stabilization, you also have the radical, right? And so what you notice, right, is that in one of them you're forming this methylene radical, right? And the mass of that fragment would be 113. Does everybody see that? And so that peak at 113 is kind of small, right? Because in order to do that, you have to generate a methylene radical. In the other case, even though it's a smaller molecule over here, the M over Z is 43, you're generating a primary radical, which again isn't that stable, but it's more stable than a methylene radical. And so you see much more of that peak at sort of 43. Okay? Okay, and so the one that everybody, it's always sort of the most difficult that everybody tends to remember for reasons, I'm not quite sure, is this sort of a Lafferty rearrangement. Okay, this is kind of a nifty rearrangement. So the peak at 58 might look a little bit interesting, but anytime you have, so alpha, beta, gamma, anytime you have a proton sort of on the gamma carbon, what you can do, and you'll see this a lot next semester, this sort of 6 electrons moving simultaneously. Again, you could do this from a radical standpoint, but in the same way that we saw that retro-Diels-Alder reaction before, where you're sort of moving, you have 6 arrows going at the same time. The same sort of thing can happen here in this sort of McLafferty rearrangement. So again, we can sort of draw from a radical standpoint. But what you'll often find is that you'll get molecules that correspond to this, and they actually end up being fairly major. And so this is sort of the McLafferty rearrangement. Again, you see that peak at 58, right? It's the second biggest peak. and this is the reason why. It does this thing called a McLaughlin rearrangement. So this is one of the, I think, the more complicated rearrangements, but clearly you can see by the spectra that this is a peak that's real, and it happens pretty readily. So again, I think it's better to think about this. The book doesn't necessarily talk about it this way. I think it's best to think about it from a homolytic bond cleavage standpoint, and so you can sort of push those arrows electrons around. Again, if you sort of rip an electron out of that lone pair, you can sort of push them around from a standpoint of heterolytic bond cleavage. Or sorry, from homolytic bond cleavage. But again, if a mechanism question comes up and it says, how does this go, and you're more comfortable thinking about it in terms of heterolytic bond cleavage, then that's fine as well. But I think homolytic bond cleavage, I think, is a little bit easier to think about, because that's kind of really what's going on. Okay? Okay, and so again, this is just sort of the summary of carbonyls, right? Or within the realm of carboxylic acid, kind of serving as both. It's kind of a summary of carbonyls, but you can imagine that a lot of this would also bear itself out with carboxylic acids. So again, these are kind of, since carboxylic acids are at the end, right? Oftentimes there's these sort of standard fragmentations that you'll see that will come up time and time again that will be an indication of carboxylic acid. And really there's only one way that they can form. Certainly you can imagine there being substitution here, but specifically if you have like a methylene carboxylic acid, you'll get something like this or something like this plus other things. But in particular you'll see this M over Z of 45, right? And there's really, if you've got a carboxylic acid, that's going to be a signature group that you're going to get, because whatever else you have over here, right? There's nothing else you can do here. So sort of M over Z 45 is that one there. And again, so here's butanoic acid. And so sort of thinking back to what we had before, this might be a type of question that might be asked, right? Here's butanoic acid. Can you, say, for example, tell or predict what the peaks are that are sort of 60 and 45? So I wouldn't just throw this up here and ask you what is this compound, right, and ask you to come up with the fact that it's butanoic acid. More likely what I would ask is a question like this, where I say, here's butanoic acid, there are peaks at 45 and 60, what are they? And again, this is sort of what we looked back before, right? So you would have to sort of gauge what these are, and so sort of know these from that standpoint. Okay, and so again, here they are. Right, sort of here's on the left-hand side is the McLaughlin rearrangement, on the right-hand side is the sort of alpha cleavage. Okay? So again, esters, this is just analogous, you might imagine. This is one that's I'm not really going to worry about too much. You'll see it in your book. It's a tropylium cation rearrangement. So oftentimes if you have molecules where you have a benzene group in them, you'll see these peaks that correspond to what's essentially a proton abstraction. And again, the mechanism of this sort of involves very complicated ring expansion, so I won't go through it that much. But don't worry about this one. I think, to just sort of memorize something. I think some of the others you guys can rationalize through homolytic bond cleavage, but this tropylium rearrangement's just one that you'll memorize, so don't bother. Okay, and so that's it for mass spectrum, or mass spectroscopy, okay? And so, I know we've got a little bit of time left, so I'm just going to sort of summarize really quickly on, guys, quiet down for a second. I just want to sort of summarize and get you guys prepared, because I think the NMR is coming up. You've got a weekend right now, and the weekend's going to be a really valuable time for studying. What I would suggest you guys all do, right, is quiet, guys, please. This is again, on the final exam, there's probably going to be a good 20% of the exam is going to be on spectroscopy. And more than likely, both of those questions will involve NMR. They might sprinkle in a little bit of mass spec, they might sprinkle in a little bit of IR. Probably, you know what, let's not worry about IR. You guys, if it ever happens that you need to learn IR, you can learn it on your own. But what I would do is I would start reading up on NMR, okay? Because you want to give yourself, as was the case in synthesis, you want to give yourself enough time to start really practicing figuring out NMR spectra. And I think you would be wise to sort of at least try to understand some of the basics before we cover it on Tuesday. Okay, so my goal to you guys would be start learning it so that on Tuesday when I start talking about it a little bit more, it's not just Greek, right? It actually might make sense to you so that you can, as soon as possible, begin to start problem solving NMR. Okay? All right.